Okay, this video session is on how to conduct an estimation. So our objective is just estimating area under the curve, which is one of the fundamental ideas behind calculus. And one of the fun questions, or to add a real-life application to this, is how many football fields can you fit underneath the St. Louis Arch? Okay, so the estimation technique that I'm going to use today is the right endpoint formula. Okay, and this is the formula that will compute this for us. But we're just going to look at the arch. Okay, so what I've done is I've taken the arch, which is 630 feet in height and 630 feet in width, and I've just kind of added a scale and broken it down into increments of about 1 centimeter, or in this case 63 feet is each increment. So I'm going to add 10 rectangles under the curve. So I've divided up my base, 630 feet, into 10 intervals. And each interval is going to be the base of a rectangle. So with the right endpoint formula, this starts at I equals 1, and the I convention always starts here, I equals 0, and this is I equals 1. Okay, so the formula starts at 1, and we're going to go to 10. So I'll start here at the 63, and I'll draw a line up until I hit my curve. And for purposes of this, I'm going to use this red line. I'm going to estimate the area underneath the red line, or the total outside edge of the arch. Okay, with the right endpoint formula here, this becomes my first rectangle under the curve. And so again, I go to my next one, in which case my next iteration would be I equals 2, and I would go to 126. And then to complete this rectangle, tie it in with this one. And this is the right endpoint method because the right endpoint of this rectangle is touching the curve. And here the right endpoint is again touching the curve. Okay, so far I have 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles, and my last rectangle is actually just going to be this flat line here, my 10th rectangle, because again the right endpoints are what's touching the curve. And this last right endpoint touches at the x-axis, so it's actually a flat line, will have no area. Okay, so the next thing I have to do is figure out how high these are. So I know each base, this is 63 feet, this is 63 feet. Now I have to figure out what the heights are. So just estimation based off this picture, this first height is about 280. Okay, this next height is about 470. This next one we'll call it 565. And the next one is 615. And then this reaches the highest point, 630. And because it's symmetric, then the heights on this other side should be the same. So here I should get 615. 565, 470, 280, and a 0. Okay, so to find out the area is just the summation of the height times the base. Okay, so when you see a formula like that, don't get intimidated. It's just base times height of a rectangle. So here, since every single rectangle is multiplied by a constant base, I'm going to factor the 63 feet out and multiply, essentially take this delta x outside of the summation. And now I'm going to sum the heights. So I have 280 plus the 470 plus 565 and the area comes out to 282,870 feet squared. And it's feet squared because 63 is in feet and all these heights are also in feet. The one tick mark denotes feet, 2 tick marks would denote inches. So now we have the area estimated to be under the St. Louis Arch. So now we want to figure out how many football fields could we fit under there. Okay, so a football field's dimensions are 120 yards, including the end zones, by 53 1/3 in width. Or in feet, this is 360 feet by 160 feet. So the area of a football field is 57,600 feet squared. Okay, and that's just the 360 times the 160 gives me 57,600. So if I take the 282,600, I'll get 4.91 football fields. And that is how much we can fit underneath the St. Louis Arch. Now keep in mind, this is just an estimation, and now we'll go to our computer program and see exactly what it would come out to be. Okay, now I'm going to go to Mathematica and we're going to refine our estimate. Okay, so what I've done is I've gone online and I've looked up the equation that models the St. Louis Arch, and I've recreated it to fit our scenario here. So here, this is my y and my x-axis. This goes from negative 315 to 315, where the peak of the arch is centered about the origin, and 630 feet in height. Okay, so this particular program that I found on wolframdemonstrations.com, and you can look this up and try it out on your own if you want to. Okay, and I've made some modifications on this to fit this demonstration. So here my delta x is 63 feet. I'm using the right endpoint method, in which case here's the right endpoint of the first rectangle, and again this is nearly a flat rectangle as our last one. So if I were to change this and say, what does the left endpoint technique look like, then it's symmetric, it's just the opposite. Okay, so here the left endpoint of your rectangle would touch the curve, this left endpoint would touch the curve, and we're still calculating the area of 10 rectangles. Okay, so let's switch back to our example. So I have number of rectangles is 10. These are my limits. We're using the right endpoint, and you see that the right endpoint gives me 292,331, and the left endpoint gives the same exact answer because we are looking at a symmetric arch, and the amount of overestimation here is equal to the underestimation here. Okay, and that's why this answer is not exact. It's just an estimation because we do have this overestimation here and this underestimation here. Okay, and the exact area is in the code above, which is the integral of the function. We're looking at 296. So with an estimation of just 10 rectangles, you see how close we got to the actual answer. So now to understand how to connect this estimation technique with integration, refine the estimation by increasing the number of rectangles. So watch as I click this plus button. Now we're up to 11 rectangles. My delta x got smaller, and you see that my estimation went from 292
to 293. So it got closer to the exact area under the curve. And watch has this the little bit of gray here and a little bit of overage here. It gets smaller and smaller as I increase one rectangle at a time. Okay, now we're at 30 rectangles under the curve, which if I'm doing this calculation by hand, this is going to take me a lot longer than it did just for 10, which is why I want to go to a computer program. But you see, when I have 30 rectangles under the curve, I have the 296,000 square feet, and now we're dealing with how accurate these last 3 digits are. Okay, so I can increase this number. Let's go to 100. And you see the gray areas here are almost gone, and this overage here gets smaller and smaller, and my answers are nearly identical, where I have 296, 615 versus 296, 658. Okay, and on this computer program I can go as high as 235 before it blows up, and this just takes a second to compute. Okay, and here's 235 rectangles under the curve, and now you see that we've pretty much calculated the exact area. We're off by a factor of 7 square feet by the computer program. So now if I were to take this 235 and make it 1,000 or 2,000 or 10,000 or 1,000,000, okay, then I'm going to get the exact area. And the idea behind estimations is we want to take that limit to infinity and put infinite rectangles under the curve and sum those together, and that's what's going to give us the integral.